Welcome to episode 6 of New Horizons. Today's guest is Dr. Mike Poland, the scientist in charge at Yellowstone Observatory and a research geophysicist with the U.S. Geological Survey. Dr. Poland specializes in volcano geodesy, using cutting-edge technologies like satellite radar and gravity measurements to monitor volcanic activity and predict potential eruptions. His work spans some of America's most famous volcanic systems, from Mount St. Helens to Hawaiian volcanoes, and he's been at the forefront of developing new methods to forecast volcanic unrest. This was recorded on March 17th. Please welcome Mike Poland. So, I'll start by explaining why this topic caught my attention. I was reading a book called The Precipice, which I recommend to everyone listening. It's about existential risk and how the probability of humanity going extinct this century is much, much higher than it's ever been in previous centuries. It covers a lot of different existential risks, like it has sections on different natural risks, like asteroids and supervolcanoes, for example, and different anthropogenic risks, like nuclear war and AI. It notes in the supervolcano section that they pose a greater threat statistically than asteroids or comets. We've done a pretty good job about asteroids and comets. NASA has entire teams tracking them down to make sure that we find any threats flying before they get here. And if one were to be approaching, we'd have some ideas, even if largely just theoretical for now, to stop it. Deflection, for example, from an ion beam or blowing it up with nuclear bombs. Volcanoes, on the other hand, we have very little idea by comparison when that could strike, and if it were to strike, there's basically nothing that we can do about it as of now. So that, in my opinion, is why I feel like there should be more work done on that and more discussion around it, because yes, even though it's very unlikely for, say, Yellowstone to erupt this century, it's still going to happen eventually, and so I think it's important to prepare and to be able to defend ourselves against that. But we'll get to mitigation and stuff later. Perhaps you could start by telling us a couple of basic things. How many supervolcanoes are there in the world, and what characteristics qualify a volcano as a supervolcano?
Well, I guess the first thing I'd like to address is the supervolcano definition, and I'll get this off the bat right away. I can't stand that term. I have a few reasons for not liking it. First, I think it's really just sort of trite. It's just sort of silly. It was like in the 90s when everyone was saying Uber this and Uber that. I've had people ask me, well, if Yellowstone's a supervolcano, what would be a hypervolcano or an ultravolcano? And just doesn't make any sense. It's just silly. Second, I think it's misapplied. The term is meant to refer to volcanoes that have had a super eruption. Now that is a term I also am not a fan of, but I'm willing to make some sacrifices in the name of simplicity. A super eruption is something that's got a size of maybe around 1,000 cubic kilometers in volume. So that's about 1,000 times the size of Mount St. Helens 1980 eruption. So really, really big eruptions, maybe super eruptions. But there are a lot of volcanic systems that have never had an eruption that big that are popularly called supervolcanoes. So that doesn't make sense, right? How could it be a supervolcano if it never had a super eruption? And third, I think it sells the wrong story about what the volcanic system is like. Take Yellowstone. Yes, it has had some massive explosive eruptions, super eruptions. But the majority of the activity at a volcanic system like Yellowstone is not very large explosions. They're lava flows. And so lava flows are far more common from the Yellowstone system than the really big explosions. So I think it sends the wrong message about what this volcanic system might do in the future. They don't only explode. They have lava flows far more commonly than they have explosions. So that's my diatribe about, why I can't stand that term. As for how many, it's really difficult because it depends on how you count them, right? I mean, is Campi Flegrei in Italy, is that something you would call a supervolcano? It's never had a super eruption. That doesn't mean that an eruption, an explosive eruption at Campi Flegrei wouldn't be impactful. So it's very difficult to say how many there are in the world just because the definition is so, squishy. But I think it's safe to say there are a few dozen volcanoes that have very large magmatic systems that in the past have been associated with very large explosive eruptions and may again in the future. And I think I would include in that volcanoes like Campi Flegrei in Italy that haven't met the criteria for a super eruption, but still would obviously have huge impacts if they did have large explosions.
Isn't there that scale? I think it goes from 1 to 8, the VEI scale. So perhaps we could, because I'll probably use the term
Yes.
supervolcano a few more times during this during this interview. So perhaps we can assume that it means an eruption of 8 or 7 to 8 or something like that. Um,
Yes. Yeah, so VEI is the Volcano Explosivity Index, and it's basically a way of it's more qualitative than quantitative. It has a number of criteria that can be used to assess it, like the height of the plume, the duration of the eruption, the volume of the eruption. So a VEI 8 is generally associated with these 1,000 cubic kilometer eruptions, but they could also be slightly smaller, but very impactful in terms of how much stuff is put how high into the stratosphere, how long the eruption lasts, and so forth. So there aren't strict definitions, but yeah, a VEI 8, that's a super eruption. Um, I think just about, no matter how you slice it, that kind of eruption is big. The last VEI 8 eruption to occur on Earth was from the Taupo volcanic region that's in New Zealand on the North Island. That was about 26, 27,000 years ago. Before that, it was the Toba eruption about 76,000 years ago. That was the most recent previous VEI 8. And the Toba eruption is probably the largest volcanic eruption that we know about in Earth's history. Now, there's a lot of Earth's history we don't know about just because it's been erased. Geologic processes will tend to take rock out of the rock record by eroding it out. But the Toba eruption was a really, really big one, far bigger than anything Yellowstone's ever done.
could you explain what flood basalt events are?
So a flood basalt is a really massive outpouring of lava, basaltic lava. So this is the kind of lava that comes out of places like Hawaii or Piton de la Fournaise in the Indian Ocean. Very fluid lava flows, so hence the flood term, and a lot of it comes out. So the last flood basalt to occur on Earth started maybe 16, 17 million years ago in the Columbia River area. So it started sort of along the eastern Washington, Oregon, western Idaho border region, and lava from that area, from that eruption, flowed all the way to the ocean. So all these famous sea stacks that you might see in the Oregon coast, parts of the Washington coast, that's lava that erupted in western Idaho and flowed all the way to the sea 16, 17 million years ago. It doesn't happen all at once. It's not an explosive event, rather like a big volcanic eruption, explosive eruption. Instead, it comes out over especially hundreds of thousands of years. So it's spread out over a long period of time. But these outpourings are so copious that the amount of gas that comes out, volcanic gas, which some of it can be pretty toxic, is huge. And so that can have some climate altering effects. But they're fundamentally different than these VEI 8 eruptions because they're not explosive. A VEI 8 eruption might happen over the course of a week, whereas these flood basalts are sort of constant for possibly hundreds of thousands of years. So you can imagine something that's sort of like Hawaii, but even more output than we see from Hawaii, order of magnitude more at least than what's coming out of Hawaii happening for hundreds of thousands of years.
Mm-hmm. And they're much more rare than something like a VEI 8 explosion.
Yeah, we can look around Earth and we can see the evidence of these flood basalts in these really, really large basaltic plains. So the Columbia River, there's Siberian traps, the Deccan in Siberia, the Deccan traps in India. There's some oceanic plateaus that are flood basalts. But these are the kinds of things that happen every few tens of millions of years, say, in terms of their recurrence. They're pretty rare events.
Mm-hmm. You mentioned the Siberian traps. I think those caused one of the 5 mass extinctions.
Yeah, they're associated with that mass extinction about 250 million years ago, the Permo-Triassic extinction. Whether or not they were really responsible, I think, is still debated, but it was a really catastrophic global event that happened in about the right time. So, it's the association there is pretty incriminating.
Mm-hmm. And then, of course, there are a lot of smaller volcanoes all around the world that do cause destruction on a more local scale. Could you give us a sense of how often those happen? Perhaps how many people die per year on average due to volcanic eruptions?
Yeah, A lot of the fatality history in volcanology is punctuated by some really catastrophic events. So in 1902, over 20,000 people were killed from the eruption of Montagne Pelée on the island of Martinique in the Caribbean. In 1985, over 20,000 people were killed in the town of Armero in Colombia when a mudflow from Nevado del Ruiz hit the town and just devastated the town. So these sort of big events tend to punctuate the timeline of fatalities to volcanic eruptions. In between then, those big events, there are less, and some research has suggested that over time there have been fewer and fewer fatalities. The reason for that is we are getting better about monitoring volcanoes and forecasting eruptive activities and then getting people out of the way. It's obviously not perfect. There's many things that happen that occur too quickly to be forecast, or they're occurring from volcanoes that aren't well monitored. But that's really the key in volcanology, is to be able to track activity, forecast when something hazardous might occur, and then get people out of the way.
Mm-hmm. What signals would indicate an increased likelihood of a major eruption, and what technologies are currently being used to monitor Yellowstone and other volcanoes?
There's a lot of different signals. I think the most common, the one that you hear the most about, is seismicity. So if you see changes in the rate of seismicity, that might indicate magma accumulating beneath the ground. As magma accumulates, you start to stress the surrounding rock, and when rock is stressed, it starts to crack, and that creates small seismicity, small earthquakes. And so the more and more earthquakes you see, especially if the rate of earthquakes increases, that's a sign of increasing stress on the rocks, and that may be because magma is accumulating. Coincident with those increases in seismic activity, you might also see inflation of the ground, like the ground blowing up like air coming into a balloon. That's a sign of magma accumulation as well, because you've got a space problem, right? If you pump a bunch of magma in, it's going to push the ground surface outward to accommodate the space needed by this magma. There are gas emissions that will be coming out of this magma as it gets shallower and shallower. There are thermal emissions. If this is happening beneath an ice-covered volcano, you might see a little bit of meltwater accumulating on the volcano, or steam vents form, a little bit of melt pits or something like that. So there's quite a few things that can be monitored when looking at a volcano that might be reawakening. This is actually happening right now at Mount Spur in Alaska, which is 50 miles or so from Anchorage. It's the closest really big volcano to Anchorage. It has erupted many times in the past. The last eruption there, 1992, disrupted air travel in the region, dropped some ash on Anchorage. It was very, very disruptive. Right now at Spur, we are seeing increased levels of seismicity. The ground is inflating like a balloon. There's some melt water that's at the summit. There's more steaming. There are gas emissions. So we know there's magma at shallow levels beneath Spur. The question then becomes, is it going to erupt? And that's a difficult question, because about half the time, maybe even more than half the time, magma that's accumulating beneath the volcano suddenly just sort of stagnates, and it doesn't make it the rest of the way out. So knowing whether or not something is going to culminate in eruption is still a challenge, but we can definitely see that there's magma accumulating, and that helps us deploy more equipment and sort of get more attention paid to the volcano, spend more time on hazards mitigation plans, making sure people know what's going on, and making sure people are prepared for what might happen if there is an eruption.
About how accurate are the predictions now? Like, what percent of the time would you say we accurately predict that an eruption is about to happen?
Well, that's really difficult too, because I don't think we are in the business of making predictions, because a prediction is very specific, right? It's a time, a place, and a magnitude, say. And that's not something I think volcanology can do at this point. We can make forecasts that a volcano is likely to become more active in the next few weeks to months. That's what's been said about Mount Spur in Alaska, that an eruption is more likely than not at this point because of all of the signs that we're seeing. It indicates that magma is accumulating at shallow levels, just a few miles beneath the surface. And based on the rate of change, the rate of seismicity, we believe that if an eruption occurs, it's likely to occur within the next few weeks to months. Generally, that has been pretty accurate. I think at well-monitored volcanoes where we have these data sets, the forecasts are reasonably accurate, that We can track these changes. We know what's happening beneath the surface, and that allows us to say with some confidence what we think the outcome might be. It's at unmonitored volcanoes that the forecasts are really, or poorly monitored volcanoes, where the forecasts are really difficult to do because we don't have enough information. It's a bit like trying to forecast the weather without having a thermometer or a barometer. All you can do to forecast the weather is sort of look outside and say, well, I see clouds on the horizon, so I think it's going to rain tomorrow. But that's not based on any special detailed knowledge of what the barometer is doing, say. So it's all about data, having the data, and that still can be a challenge in some places for volcanoes.
Are people starting to use machine learning to get higher accuracy forecasts?
Yeah, they are. I don't think machine learning is yet to the stage of using it for forecasting specifically, but it's being used for detection of signals that maybe humans would see or wouldn't have the time to identify themselves. One example is in seismicity. Now, right now, the state of the art is a computer can look at a seismic record and pick out, okay, looks like I think this was an earthquake. And they flag that for a human analyst to go back and say, yes, that was an earthquake, or no, that was road noise or bison stampede or something like that, right, that caused the ground to shake. Machine learning has shown some promise at being able to identify earthquakes just as accurately as a human and get smaller events that might otherwise be missed. And so we are on the cusp of starting to deploy machine learning algorithms for real-time seismic locations, and that will really change how we're able to locate and interpret earthquake activity, not just at volcanoes, but anywhere. We've also deployed it to looking at satellite images. We are getting, more satellite images than we could ever hope to look at in terms of flipping through and looking at thermal images, or looking for changes in visual images, or looking for ground deformation in radar images, which is something that we can detect in these with radar data. But by deploying these machine learning algorithms, we can comb through huge amounts of data, hundreds of thousands of images, without humans having to look at them, and then the routine can flag things that it thinks are anomalous. And maybe it flags 100 things out of 100,000 images, and maybe only 30 of those 100 are real signals that we might need to be worried about. But that's still a heck of a lot better than having to look at 100,000 images manually. So machine learning, these AI approaches, they're really starting to change the game in data analysis and interpretation. And eventually, maybe we'll see their deployment to some forecasting, but that's not quite there yet.
Are there other ways that these technologies that are used to monitor volcanoes have evolved over the past few decades?
I think volcanology used to be very data poor. You used to have to really earn the data. I mean, you had to go out and collect it in the field, and that meant having teams of people measuring the elevation of the ground surface at various points. You would have to spend weeks with a team of 5 or 10 people to get annual data that showed what a small area, say of Yellowstone, was doing in terms of vertical deformation. Was it going up or was it going down? Now we can use satellites to get the same information pretty much anytime we want. So it feels like over the course of just a few years, I mean, this transition really happened sort of in the late 90s to early 2000s. We went from being data poor, not having that much thermal data or deformation data or even seismic data at volcanoes, to becoming pretty data rich. And that has changed the way volcanologists have to approach things. Instead of struggling with just a few data sets, now it's sort of like drinking from a fire hose. There's a lot to look at, and that's where these AI and so forth approaches are now starting to come in handy, where we need to catch up with the amount of data we're collecting.
Tell us about Bayesian event trees and the ways you try to calculate the probabilities necessary to make these forecasts.
Event trees are sort of a way that we can attempt to make some forecasts. The volcanologists want to get information to people, the public, emergency managers, and it needs to be actionable information. And so a lot of that then centers on what is the probability of a certain event. So one way we calculate that, and when we go through the thought process of trying to understand how you would get a probability, is use something called an event tree. And so you imagine it looks like a kind of a tree with branching nodes, And at each node, you're asking a question. So the first question might be, is a volcano restless? Yes or no? Well, in a place, let's say Mount Spur, you've got a 100% answer that yes, it's restless. We know it's restless. There's seismic activity, there's ground deformation. So yes. So question 2, is it magma that's causing the unrest? At Spur, we're very confident that it's magma, 100%. At a place like Yellowstone, we know there's seismicity at Yellowstone. The ground goes up and down. There's gas emissions. But guess what? Magma moving around is not the cause of the seismicity that we see at Yellowstone every day. So at a place like Yellowstone, we would say 100% no, magma's not the cause of the earthquake swarm that's happening, unless that changes in the future. At a place like Spur, it's 100% yes. So now we're at 100% yes for Spur, and then you begin asking questions, all right, what is the probability it's going to erupt? And that may be based on perhaps analogs. Like we know there's a lot of volcanoes like Spur around the world, and in most cases, maybe 75% of cases like Spur right now, it culminates in an eruption. And so we say, okay, 75 yes, 25 no. And you fill out all of those things until you get down to the level of saying what a certain probability of a certain impact is, a mud flow or an ash flow or a lava flow impacting a certain area. And then you can provide this information to the public and emergency managers, like the probability of a certain amount of ash fall in Anchorage is X%. And that's actionable. That can help people decide what sort of precautions they might want to take, whether or not the airport should have some contingencies for whether or not there would be ash that would disrupt flights, and so forth. So that's how event trees work. Bayesian event trees introduce a different kind of statistics to this that allows us to be a bit more quantitative and calculate uncertainties and carry those uncertainties through as well, because it's easy to sort of sit there and say, well, it's 50-50 that something's going to happen, but there's uncertainty in all these numbers. And when we get into Bayesian statistics, we can start to accommodate some of those unknowns, which, there's a lot of them. We can't, unfortunately, see beneath the surface directly. And so a lot of what we're doing is we're inferring what's happening beneath the surface based on what we're seeing at the surface, ground deformation, seismicity, so forth. So accounting for that uncertainty is a challenge, but important.
There have been a few cool stories about how researchers or the people monitoring a volcano were able to notice that something was about to happen, and people were able to be saved or evacuated just in time. Perhaps you could tell us a couple of those anecdotes?
The one that boggles my mind is this small island in Alaska called Kasatochi. I think it was maybe in 2017, 2018, around about that time. There were a couple of wildlife biologists, because this was a area where there were a lot of nesting birds that would seasonally migrate through. And the wildlife biologists sort of noticed suddenly there's a lot of seismicity. Now, Kasatochi was unmonitored, but these biologists that were on the island feeling earthquakes, and they noticed changes around them. So they were effectively the monitors, and they started radioing out, hey, something's going on. They were picked up by a boat and pulled off the island within hours, maybe even an hour, of an eruption that basically swept the entire island with ash flows. They would have almost certainly been seriously injured or killed had they been on the island when the eruption happened. So there was a case of an unmonitored volcano, but the unrest got so strong that the people that were on the island felt it and were able to get off the island, fortunately, just in the nick of time. So it pays to be attentive to your surroundings and what's going on around you.
Taking Yellowstone as an example of a supervolcano, even though you don't like that term, what kind of destruction would it cause if it erupted? Would all of the nearby states just be covered in magma and the entire U.S. covered in ash? Or?
Well, if you believe some of the animations and graphics I've seen, most of Wyoming would be a gigantic crater or something like that. It depends very much on the style of eruption. If it was a lava flow, as several dozen lava flows have occurred since the last really, really big explosive eruption, lava flow would impact the park itself and very little else. I kind of suspect that if there were a lava flow eruption, it would be more of a tourist attraction than anything else. And people would be flocking to see this thing because it would be unbelievable. There may be a small explosive onset. Some of these lava flows are associated with ash layers, but they're not massively thick ash layers. So you might have an explosive onset, possibly something on the size of Mount St. Helens 1980, maybe smaller, that would deposit some ash, and then you'd have this lava flow that might come out. And that lava flow might be active for decades. It's difficult to know how long those go. So that's sort of a very local effect. And if there's a little bit of ash, it would affect things downwind. If it were a really large explosive eruption, then yeah, you would see really big impacts for the couple hundred kilometers around the center of the eruption. It would not, completely devastate every state in the area, but the surrounding area would certainly be swept by these ash flows out to tens of kilometers at least. The ash fall from that eruption would depend a lot on the volume of it, how high the ash got, but you could imagine that there would be many tens of centimeters of ash fall in that vicinity and extending out for maybe a few hundred kilometers. And that would have a huge impact on agriculture, water, electricity. And then the farther away you go, the less and less ash there would be falling. But even just a few millimeters of ash can have an impact on something. So if there were a really large explosive eruption, it would definitely have a huge impact on the U.S. It would not make the entire, continent of North America unlivable immediately. No, that's not how it works. But the serious impacts would be right in the vicinity, and then there would be some longer-term impacts as you got away from that. And it would also impact global climate. You put that much ash and gas into the atmosphere, it will reflect sunlight. And so you would see a drop in global temperatures that would have an impact on growing seasons, agriculture worldwide. So eruptions like that definitely have a global impact, even if you don't have any ash actually falling on you.
Yeah, the scariest part is the volcanic winter. Like you mentioned, it would affect things like crops. Do you think there's any chance that civilization would collapse or not really?
Well, it's an interesting question. I mean, we as a species have lived through two super eruptions. Toba, 76,000 years ago, and the one from the Taupo area in New Zealand, 26,000, 27,000 years ago. And we're still here, right? We obviously made it. There were other species, hominid species, that were like a couple of islands away from Toba, and they survived. So clearly it can be done. Our Achilles heel might be dependence on technology. So I think it would be devastating globally if something like that happened. I don't think it would mean the end of our extinction, because we've tried that experiment a couple of times before and we haven't gone extinct yet. But it's not something I'd want to live through, no.
Yeah.
And actually, I should add something else there, if that's okay. There's this thing that was circulating a few years ago that got popularized as the Toba catastrophe theory. And the idea here was that Toba erupted, and about the same time there was a genetic bottleneck in humanity. And so the association was that this eruption was so bad that all of humanity at the time was whittled down to a few individuals, maybe a very small population in Africa, and then it came back. Humanity came back. That idea got really popular, and suddenly it was, Toba almost did us in as a species. Well, subsequent work into that idea is sort of casting some doubt on it. It doesn't look like the climate impacts were possibly as bad as originally thought. The timing of the genetic bottleneck doesn't really line up with the eruption in quite the way that was originally assumed. Dating got a little bit better, and it doesn't quite equal. So there's a lot of doubt now about Toba catastrophe theory being real, and I think more evidence is piling up against that than for it. So but that's the problem with a lot of these ideas, is they make a real splash when they come out, and you get lots of documentaries about them and so forth. And then more information comes out, and maybe there's some uncertainty and some doubt is cast on it, but there's no documentaries that come about saying, well, maybe this was a little bit premature and we don't think this idea, addressing the controversy that's come. And that's often swept under the rug a little bit. So I'm sure there's still a lot of people out there that have heard this and aren't aware that maybe it's not quite as supported as we originally thought.
Interesting.
That's the way science works, right? Come up with ideas, test them, and sometimes it sticks and sometimes it doesn't. That's the way it's supposed to work.
Yeah. Now for my favorite part of the conversation and possibly your least favorite. uh, there was a NASA drilling proposal that received a
Ah,
fair amount
yes.
of attention a few years ago. They suggested a few different ways to intervene, like a few different engineering approaches in order to decrease the chances of a large volcano erupting. Could you explain that and the main reasons why this approach is problematic?
Hmm. Oh man, do we have to go down this road? Yeah, I guess so. Yeah, so the idea that was proposed was, well, we'll drill into Yellowstone specifically. I don't know why, the report makes the point of saying, as you noted right off the bat, a very large volcanic eruption is far more likely than an asteroid impact, right, to really do a number on Earth. But then they really zeroed in on Yellowstone as if Yellowstone's some sort of boogeyman. And that, you know, for one thing, Yellowstone's magma chamber, we know from seismic imaging techniques, sort of like taking an MRI of the Earth, is mostly solid anyway. So this is not a problem that needs to be solved right away. There's other volcanoes that are far more likely to erupt. So the focus on Yellowstone was a little bit misplaced. But regardless, the idea was drill into Yellowstone, drill into the magma body, start pumping cold water in there. Cold water will act to cool the magma reservoir, even though it's already cool. We're going to ignore that part. And it will, at the same time, the water is heated, by all that magma down there. And so it comes back up to the surface as steam, turns turbines, and you make energy. And so you would get all this energy, and you would reduce the threat of a volcanic eruption from Yellowstone at the same time. Well, there's there's more than a few problems with this, but um, there's a sort of the physicists love to say things like there ain't no such thing as a free lunch, right? You don't just get something for nothing, and in order to get water down there, you'd have to basically pump it up from the Ogallala aquifer, and most of the farmers in the Midwest probably would be, you know, unhappy about losing all their water just pumping it into the ground at Yellowstone. Yeah, you'd make some energy, but you'd also have to spend an awful lot of energy pumping all the water up to Yellowstone, which is the highest area in the Rockies on average. So that you're probably not going to make a lot of free energy because you're going to spend a lot. And on top of that, you're not really going to cool anything because the heat engine for Yellowstone is sort of constantly churning. It's a bit like trying to shut off the burner on a stove by using an eyedropper to pour cold water into a pot of boiling water. Now, maybe eventually you would start to affect the temperature of that water, maybe if you're doing the eyedropper fast enough, but the burner is still on. You're not turning off the burner. You're not dripping water on the burner. So this whole principle is kind of flawed from the start, and it wouldn't result in any real benefits. On top of that, the most likely thing that would happen is that you would begin shutting off all of these thermal features in Yellowstone. Old Faithful would stop erupting. Grand Prismatic Spring would cool down and not become near as prismatic. This happens around the world in places where geothermal development has happened. The largest geyser in the world, the tallest active geyser in the world, used to be in New Zealand. A geothermal operation started not far from the geyser, and the geyser stopped erupting. So you can imagine that potentially happening in Yellowstone, where this sort of geothermal operation would kill off the geysers and hot springs that are the reason it's a national park. One of the reasons, anyway. So it would have a lot of negative impacts. Um, and the benefits, it's not really going to do much in terms of cooling the volcano down. As it's a bit like trying to, I don't know, trying to stab an elephant with a toothpick. It's just not gonna do much.
You mentioned that you don't think Yellowstone is a big concern, but I heard this statistic, and I don't know how accurate it is, that Yellowstone erupts every, like, on average 600,000 years, and that it's been about 600,000 since the last one. So
Ah, yes, we're overdue.
yeah.
That's, I think this might be the most persistent and common misconception about Yellowstone. Um, I don't know where the 600,000 number comes from. If you look at the last three really large explosive eruptions, they actually occurred about 725,000 years apart on average. So by that token, we still have kind of a ways to go. But that's 3 events. That's 2 intervals, right? That's not a whole lot of numbers to base good statistics on. If you go back further in time, there's more time between eruptions, so the time frame gets even longer. So that number is kind of made up out of uncertain sources. On top of that, volcanoes don't work on schedules. You can say there's an average recurrence interval, but fundamentally the volcano will erupt when there's enough eruptible magma in the subsurface, that is magma that's pretty molten state, charged up with gases. Well, that doesn't exist at Yellowstone right now. There also needs to be pressure to get that magma to the surface. Also not a condition at Yellowstone right now. So we don't have the conditions that would support an eruption anytime soon, and it would take a while to generate that eruptible magma and start building that pressure. So it's just not something that is an immediate issue. I liken it, there is some long-term statistic. Maybe it's once every 725,000 years on average, or something like that. But the way I would liken this is the odds that you're going to win the lottery, or you're going to be struck by lightning. There's a statistic for that, right? There's a 1 in whatever number that you're going to get struck by lightning or win the lottery. But if you never buy a lottery ticket, those odds don't apply to you, right? You're never in a situation where you're going to win. What are the odds of getting struck by lightning on a gorgeous sunny day? The statistic might say one thing for the long term, but the immediate term says 0. And so that's where we are now with Yellowstone. We're, not worried about lightning because it's a gorgeous sunny day and there's no clouds on the horizon, or we haven't bought the lottery ticket, so we're not worried about our odds of winning, or losing, I guess, in that case. So regardless of what the statistics may be for the long term, the short term is what really humanity cares about, or human life, and that's just not a concern at Yellowstone. The conditions aren't there. The real hazards in Yellowstone on human timescales are hydrothermal explosions. These are steam explosions. They're not driven by any changes in the magmatic system. They're mostly kind of pressure cooker situation where you seal up a bunch of conduits and steam pressure builds and then kaboom. And that happened in July last year, 2024, in Biscuit Basin on a beautiful sunny day. There were a lot of people in the area. Fortunately, no one was hurt, but that was very well recorded. There's some spectacular video of that. The other big hazard on human timescales in the Yellowstone region is a strong earthquake. The largest earthquake ever recorded in the Intermountain West happened right on the border of Yellowstone National Park in 1959. It was a magnitude 7.3. Magnitude 6 and 7 earthquakes will happen there. It wouldn't surprise me at all if one happened in my lifetime. So those are the real hazards that are kind of human timescale hazards in the region.
I see. And so is there no way to somehow slowly suck out or extract the magma over time?
I don't see it happening. It's that toothpick with the trying to bleed an elephant with a toothpick. The magma system there is humongous. It is massive, and it's mostly solid, but it's still hot, still really hot. So there's just, I don't see how you're gonna, with any sort of realistic technology, going to bleed that off. It's also not, I think part of the problem with this is that most people envision magma chambers to be these cauldrons of molten material. And I think this is sort of perpetuated by volcanologists who draw red balloons beneath volcanoes, right? Well, they're not red balloons. They're not these sort of half full or completely full caverns of molten rock. Rather, a magma chamber is a really complex mixture of some melt, some crystals and other solids, some gases that are sort of swirling around, so it's mushy. And in some cases, the solids so overwhelm the liquid part of it that it's basically stagnant. It's sort of like concrete that's 90% solid. That's not going anywhere. It may not be 100% solid, but 90% solid concrete is not going anywhere. So that's the sort of situation we're in Yellowstone, is we've got this really complex, large mixture of mostly solid materials, crystals and so forth, a little bit of melt, a little bit of gas, all mixed together. It's not something you can pop in terms of, we're going to just prick it and then let the air out of it or let the pressure out of it like a balloon, because the pressure doesn't accumulate in such a body in a uniform way like it does in a balloon. It's a mess. It's like, I don't know, poking a balloon of mostly solidified concrete or something like that.
Yeah, and I guess people could think about theoretical approaches that we could do if we had like unlimited resources and technology available, but then there's also government as a limiting factor. Like even if we did think of something like that, then no one would ever want to like invest that long term in something that's not an immediate risk.
Yeah, I think this is one of those societal questions that, like, okay, let's say you wanted to approve this, like drilling in the Yellowstone project and pumping water down and turning off all the geysers and so forth. The cost of this is going to be astronomical. And the study suggested that, and I think their timescale is off because, again, you're not hitting the burner. It would be 10,000 years that it would take to cool Yellowstone down. Again, if there's no additional heat coming in. Well, in that 10,000 years, how many Category 5 hurricanes are going to hit the southeast U.S.? How many Category 5 hurricanes are going to hit in our lifetimes? I bet it's more than one. And so I think there needs to be some consideration of the kinds of things you're going to neglect in order to deal with this problem, which isn't really much of a problem. There's flooding and, extreme heat. It has is far more common and impacts a lot of people every year versus something that's unlikely to happen in tens of thousands of years. So in some ways, I think the concern about Yellowstone as a hazard, we got to do something about it, is really misdirected, because there are some things we can do about hazards that affect us every year. Building better levees, or strengthening our response to hurricane and flood preparedness and so forth. That would save an awful lot of people. And being worried about a Yellowstone eruption that's it's something that's showing no signs of erupting anytime soon, I think it's a misplaced priority. It doesn't mean that we don't need to be aware of what's going on at Yellowstone. Volcanoes give warnings. That's one of the reasons we monitor them. And there are other things happening in Yellowstone that we need to be aware of, like these earthquakes and these hydrothermal explosions. We can also apply things we learn in the Yellowstone area to other volcanoes, like Campiflagrei in Italy, which is very restless, or Taupo in New Zealand. So monitoring a volcanic system like Yellowstone is not without a lot of benefits. But I'd suggest that it's not necessarily the world-ending threat, the immediate world-ending threat that it's sometimes made out to be.
Well, very interesting stuff. Is there anything else you think is worth sharing?
Well, I guess if people are really interested in Yellowstone, we do try to put out a lot of interesting stuff about the volcanic system or the geology. The Yellowstone Volcano Observatory does these articles called Caldera Chronicles that comes out every week, and we always try to answer questions that people have, because there's obviously a lot of not the greatest information floating around out there, and we understand people really want to know about it. So we're always happy to answer questions, and we try to put out a lot of information about current seismicity and things like that, in addition to geologic history. So if people are interested in knowing more, the Yellowstone Volcano Observatory website and USGS Volcanoes social media channels generally put out a lot of information that hopefully people find interesting.
Well, thanks for answering the questions. It's very, very fascinating work.
My pleasure. Thanks a lot.